Ladies and gentlemen, welcome to this lecture on alternating current charging or AC charging of electric vehicles. I'm Gautam Ram and a postdoctoral researcher at the Delft University of Technology. In this lecture, we are going to learn about four things. First, what are the key parts of an electric vehicle AC charger? Second, how does AC charging work? Third, what are the types of connectors used for AC charging? And lastly, how can AC charging power be calculated? Let us first look at the parts of an AC charger. In its simplest form, AC charging uses an onboard charger to convert electricity from AC power from the conventional AC grid to direct current or DC power to charge the traction battery pack. Cars have a standardized vehicle inlet, and a charging cable is used to connect the vehicle connector to the infrastructure socket of the AC charging station. In some cases, the charging cable is permanently connected to the charging station as well, similar to a petrol pump. For a safe and reliable charging process, there should be several essential components in an AC charging station. Let's look at it by following the power flow from the charger to the electric vehicle. When the charging station and the EV are first connected, the charge controller in the station communicates with the EV. In this communication, information regarding the connectivity, fault condition, current limits are exchanged between the charger and the EV. Safety interlocks are used to ensure a safe charging process and to stop the charging in the event of a fault condition or an improper connection between the EV and the charger. When the AC power is provided to the EV, the onboard charger has a rectifier that converts the AC power to DC power. Then, the power control unit appropriately adjusts the voltage and current of the DC converter to control the charging power delivered to the battery. The power control unit in turn gets inputs from the battery management system or the BMS for controlling the battery charging. The battery management system monitors the key battery operation parameters like voltage, current, or temperature. It then provides inputs to the power control unit to control the charging power delivered by the DC to DC converter. Apart from that, there's a protection circuit inside the onboard charger. The BMS triggers the protection circuit if the battery's operating limits like the voltage or current are exceeded, thereby isolating the battery if needed for its safe operation. Now, with a basic understanding of the AC charging process, let us now look at the four main types of AC charging connectors which are used around the world. The EV industry has unfortunately not agreed on one specific connector, so depending on the car brand and the country, the connector varies in shape, size, and pin configuration. One of the main reasons is the difference in AC voltage and frequency around the world. For example, in the United States of America, power is supplied using a 120 volt 60 Hz single phase AC or a 240 volt 60 Hz dual phase AC. On the other hand, in Europe, 230 volts 50 Hz single phase AC or 400 volts 50 Hz three phase AC is used. Due to these differences in both voltage, number of phases, and frequency, it leads to differences in charges between the two regions. Generally, an AC connector has two or more larger pins to transmit power and a few more smaller pins for the sake of communication. There are four types of AC connectors which are used worldwide, namely the Type 1 connector, which is mostly used in USA and Japan, the Type 2 connector, which is mostly used in Europe, including those of Tesla cars, the Type 3 connector, which is used in Europe but is being increasingly phased out by the Type 2 connectors, and finally, the proprietary connector used by Tesla for its cars in the USA. Besides this, China has its own standard for AC charging, which is similar to the Type 2 connectors. Now, let us look at how these connectors are different by delving into the details. In this picture, we can see a type 1 vehicle connector which is specifically used for charging with single phase AC. It has a round housing consisting of 5 pins. There are 2 pins L1 and L2 for the single phase AC. There is 1 pin for the protective earth, and there are 2 signal pins which are used for communication, which is the proximity pilot, or in short referred to by PP, and the control pilot, which is in short referred to as CP. The proximity pilot is used for ensuring connectivity between the EV and the charger, and the control pilot is used for controlling the charging current. The maximum voltage and current rating of this charger of type 1 is 120 volts or 240 volts single phase AC with a maximum current rating of 80 amperes. Let us now look at the type 2 vehicle connector, which is also commonly referred to as the Mennekes connector. The type 2 connector, which is used all over Europe, is circular in shape with a flat top edge. The top row consists of 2 pins for communication, as we've seen earlier, namely the proximity pilot and the control pilot. The middle and lower rows consist of 5 pins for AC power transfer. There are 3 pins used for the 3-phase AC connection, phase A, phase B and phase C, and then there is 2 pins which is used for the neutral and for the protective earth. The maximum voltage and current rating are single phase 230 volts up to 80 amperes, and in case of 3-phase, the voltage is 400 volts and the current can be up to 63 amperes. Next, we look at the charger used by Tesla. In case of Tesla, they use a proprietary connector in the US as shown in this picture. In Europe, Tesla cars use the same type 2 connector for charging the cars. Unlike other car manufacturers, Tesla is unique that it uses the same connector for both AC and DC charging. With this US Tesla connector, a maximum charging power of 17.2 kilowatts can be delivered to the car from a 240 volt AC outlet. You might have noticed that when I mentioned about the type 1 and type 2 connectors, that there are 2 communication pins, the control pilot and the proximity pilot. Let us now look deeper into their functions. The proximity pilot checks if the vehicle connector is connected properly to the vehicle inlet, the connection. If the connection is not properly established, the proximity pilot will detect this and the entire charging process will be disabled for safety. In case of the control pilot is used for controlling the charging current. The control pilot continuously sends a pulse width modulated or a PWM signal to the car. In this way, it tells the car the maximum current that can be drawn from the charging station, which is Imax. The car then uses this PWM signal and then draws the desired current, IAC, and it ensures that as long as this value is smaller than the maximum charging current, Imax. Now that you have seen about the different AC charger types, let us now look at how we can calculate the AC charging power. This is quite simple. The calculation of the single phase AC charging power is a product of the single phase AC voltage VAC and the grid current IAC. The 3-phase AC charging power is calculated as the root 3 times the product of the line to line 3-phase AC voltage V3AC and the grid current IAC. For AC power calculations, it is important that the root mean square or the RMS value of the voltage and current are used. Also, we should keep in mind that not all the AC charging power is actually delivered to the traction battery. This is due to losses in the charging system. Typically, onboard chargers have an efficiency of 90 to 95% and the rest of it is lost due to losses in the conversion. Now, based on the AC charging power that has been introduced, let us now look at the charging time versus the charging power for different battery sizes. Assuming no losses, the charging time TCH can be calculated as the battery capacity EBAT divided by the charging power PCH. The graph on the right side shows the required charging time for different charging powers in the case of 2 battery sizes, a 30 kilowatt hour battery and a 100 kilowatt hour battery. The data labels shown are commonly used EV AC charging powers. As we can see, if we charge a battery with higher powers, say 22 kilowatts, a couple of hours are still required to charge the battery fully. This is especially true for the 100 kilowatt hour battery. Considering there is limited space and weight for the onboard charger and for its power, there is an upper limit for the maximum AC charging power that can be delivered. This is why if we need to charge the car battery faster, we need to move to fast charging of 50 kilowatts and above using DC off-board chargers. So, to wrap up, you have now got an idea about the parts of an AC charger and the 4 AC charger connector types. We also looked at the role of the proximity and control pilot in the control and protection of the charging process. Finally, we saw how a simple formula could be used to estimate the charging power and charging time for AC charging. Thank you.